Hey guys, how's it going? Hope you've had a good weekend. Let's get into the next video lecture. Okay, so this week we're looking at deflection and also using deflection to enable us to find the reactions for statically indeterminate problems. So up until now, I think most of your work where you've had to find reactions at supports using equilibrium equations, all of those have been statically determinate. So you could just use the equations of equilibrium to find all of the reactions. What we're going to look at probably in the second part of the video is the method for enabling us to calculate reaction forces and or moments when we have a statically indeterminate problem. So when we've got more unknowns than we have equations. Okay, so lecture objectives. As I said, to first look at deflection and slope of beams and shafts at specific points using the method of superposition, and then to solve for statically indeterminate problems. Okay, so brief outline of the parts of the lecture. So a review of the beam deflection and slope by integration. So you would have studied this in mechanics of solids. Look at beam deflection and slope formulae. Then we'll look at method of superposition, and then look at some examples of calculating deflection and slopes using superposition. And then in the next video, we'll look at statically indeterminate problems. Okay, so I'm not going to read through all of that. You can read that for yourself, and I've pretty much said this part here. So just a reminder about the elastic curve. So the elastic curve is the deflection of a line through the centroid of the cross-section of the beam. Okay, and the governing equation characterizing the shape of the deformed beam is this differential equation here. So the differential of the displacement squared with respect to x is equal to bending moment as a function of x, so position in the beam, divided by Young's modulus and the moment of inertia. Just a reminder, so this goes back all the way to Introduction to Mechanical Engineering, or Mechanical and Mechatronics Engineering, where we first looked at equilibrium and looked at supports. So a support that resists a force, so such as a pin, so it stops the point from moving. So if we have something like this, right, at here in my left hand, so you'd see it on the right. This support stops the beam from moving left or right and up and down, but there's still rotation allowed. Okay, whereas a support that resists a moment, so if I hold it like this and apply a load here, then that support is resisting a moment, okay, and that is restricting the rotation here. Okay, so where it starts off as flat, I apply the load and it stays horizontal at that support. Okay, so that should be just a revision from earlier work. And generally we have four methods to determine the deflection and slope at specific points on beams and shafts. So method of superposition, which we're going to look at in this lecture and in this subject, and the other three methods are the integration method. So you would have studied this in mechanics of solids. Discontinuity functions, you may have covered this in mechanics of solids, and then moment area method you probably didn't cover in mechanics of solids. Moment area methods is usually reserved for statically indeterminate problems. But we're not going to look at that in this subject. That's another topic that you can look up if you need to later on. Okay, so elastic curve review. So we have here a loading, and then over on this side of the slide, we've just got a general deflected shape showing that we've got some bending moments causing it to deform. So we have our elastic curve and we have radius of curvature along the beam. Okay, so the relationship between curvature and the bending moment is that 1 over the rate over the curvature is the bending moment as a function of x, position along the beam, divided by Young's modulus and moment of inertia. Okay, so this rho symbol is the radius of curvature at a specific point, and for small deformations we have these relationships between bending moment. Okay, so you have drawn bending moment diagrams before, and we did a bit of that when we were looking at stresses in previous lectures. And we also have the shear diagram, or the internal shear force, and then we have the shear diagram, and then we also have the loading. So here we have a distributed load and the relationship between the deflected shape. So here we have the deflected shape given by the symbol V, right? So the vertical deflection here. The relationship between the radius of curvature, or the curvature, and the deflected shape. So normally we just look at 1 over rho is equal to d squared y upon dx squared. This is actually a simplification. Right, so if you go through the maths properly, then what you'll see is this is the true and accurate relationship, but this dy dx, because this is small and because it's squared, this becomes very small, and so we simplify this to just 1. So we have 1 over the radius of curvature is d squared y upon dx squared. Okay, so you need to get used to the fact that we're using simplifications, and always check before you use an equation what the simplifications and assumptions were that led to the equation or formulae that you're using. Okay, so integration, we can do this. So you would have seen how to do this in mech solids, not mechanics of solids. So I'm not going to go through this in this video. Again, it's just revision of what you did in mechanics of solids, reminding you about signs and things. So what we're going to do is to make use of the standard formulae for, or the formulae for standard beams and loadings. Okay, so here we have 6 simply supported beam slopes and deflections. Okay, so simply supported with a load in the middle, simply supported with an offset load, simply supported with a moment at one end, simply supported with a distributed load halfway across, and so on. Okay, and we've got 6 cases for cantilevered beams, so fixed at one end, free at the other. So this is our cantilever beam with various loadings, and for each of those we have equations that we can look up, or formulae that we can look up for the slope at various locations. So it might be at a given point, or it might be the maximum. So here we've got the maximum slope, the maximum deflection, and also we have the elastic curve. Okay, so we can calculate the deflection at any point in the beam. So we'll come back to these. So I'm just going to skip through these for now. So these are from the Hibbeler textbook, and if you're using the Beer and Johnson textbook, this is the table with the same standard beams and loadings, and the equations for elastic curve and the deflection and slope at various points in the beam. Okay, so the principle of superposition simply says that if you have 2 loadings, then you can work out the deflection and slope from one loading, and then work out the deflection and slope for the other loading, and you just add them together. Okay. Okay, so if we have something like this, for example, so we've got a simply supported beam, uniformly distributed load, and a point load somewhere. Right? We can't look up a standard case for this, right, and get the displacement at D or anywhere else. So what we can do though is to separate it into two parts. So we have the simply supported beam with a load somewhere along the beam. So in our table we have this standard case, and we also have the standard case of a distributed load. Okay, so we can just simply add those two things together. Important thing to note though is that this simple addition of the two deflections or slopes from the two loadings is only valid if the force displacement relationship is linear. So if you have a non-linear force displacement relationship, so if you have a non-linear material, or more likely if you have large deflections, okay, so it's a geometric non-linearity, then you can't do this simple addition. Yep. Okay, so here's a quick example. So we have a cantilever beam with a uniformly distributed load over half of the length, but it's distributed over at the free end. Okay, so apply the principle of superposition to determine the slope and deflection. So you think, hang on a second, there's only one load here. How are we going to use superposition? So what we can do is to note that this loading here is equivalent to if we have the loading distributed across the whole length. Yep. And then if we consider between A and C, we have a force or distributed loading in the opposite direction. Okay, so this plus this is equal to this loading. So if we calculate the deflection from this one and the deflection and slope from this one, add them together, we should get the deformations for this case that we don't have a standard solution for. Okay, so let's have a look at this. So loading 1, that's fairly simple. We can go to our standard case here and we can look up our table. We can say, yep, we've got that. We can work out deflection and slope, no problem, right? Because the maximum deflection and the slope at the end is given. Okay, so we can simply put that in. So that is there, and our deflection is simply that. Okay, easy enough. All right, loading 2. So that's this case here. Now in the Hibbler table, there's no case like this. Okay, in the Beer-Johnson table, there's no case like this. In the Hibbler table, there is. But we're going to assume that we don't have a standard case that looks like this, so we can demonstrate how you might do things if you don't have a standard case. For example, if you have, if this was not half the length of the beam, if this was say 1/3 or 2/3, then there is no standard solution. Okay, so you'd have to do something different, and what you could do is what we're going to show you here. All right, so we're going to look at the displacement here at point, or the slope and displacement at point C. Why are we going to do that? Let me go back to the full screen here and show you. All right, so if I take my thing here again, if I push here, right, what you should see is to the left of my finger, you'll see that the beam isn't bending. Okay, it's a straight line. Okay, so we have bending between my two hands, but from my finger out to the free end, it's just rotating, yep, as a rigid body. Okay, so as you're looking to the left of my finger, that's a straight line. Okay, so, and we can, if we know that angle, okay, so if we know this length, and we rotate that through an angle, we can work out that deflection, yeah? So it's just angle times the length, right, where the angle's in radians. Okay, and the slope at the end, because it's a straight line from my finger to the free end, the slope at the end here will be just simply the same as the slope at point C. Alright, so let's see how that works. Okay, so first part, C to C, we can just get that from this equation, slope at the end, but we need to be careful, right? Our length here is not L, but L over 2. Okay, so if we substitute L over 2 into here, 2 to the power of 3, or 2 cubed is 8, so 6 8s are 48. Yep. And then our slope is this equation, right? Because we're looking at point C here. We want to know what this deflection here is. So again, our length here is L over 2. So L over 2 to the power 4. 2 to the power 4 is 16. 8 times 16 is 128. Okay. And when we're doing these problems, you can indicate the directions either by using the signs as given in the formulae, or you can just draw arrows and follow those arrows as you work through the problem. Okay, so now looking at point B, which is at the end. So as I said, the slope at the end of the beam will be equal to the slope at point C for loading 2. Okay, because we've just got that. And at my finger, right, my finger here, from there to the end, it's a straight line. And then for our total deflection due to loading 2, we have the deflection at my finger, right, plus this angle times the length from my finger to the free end, which is L over 2. And if you substitute that in here, that's what we get. Right, and as I said before, Hibbeler actually has this as a standard solution in the table in that textbook. Right, so if you look that up, you can see that we get the same, or that table indicates that we've got the correct result here. Yep. Okay, so a total deflection at point B is simply combining the two solutions. Right, so add them up. So we have using our sign indicating negative as downwards. Okay, so loading 1, negative, plus loading 2, which is pushing up, gives us that as our slope. And right, we can see that this is correct because we know that this is going to be in the negative direction, right, because it's downwards. So just make sure we got our signs right over here and our sums and algebra right. And then our deflection, total deflection at point B, deflection from loading 1 and deflection from loading 2. Okay. And again, that's negative, noting that negative is downwards.